Thank you everybody for being here again today for this periodic seminar series. Today we have a talk by Davide Compagnin. I hope I pronounced your name correctly. And he's going to talk about experimental evaluation of optimal schedulers based on partitioned proportionate fairness. I just have to mention that Davide comes from University of Padua in Italy, where he's working on the Proxima project with Professor Tullio.
Yes.
Okay, you have around 30 minutes.
Thank you. So, hi, you all. Today I'm going to present the work I've done during the first part of my PhD program concerning the implementation of RAN and QPS, the reduction to uniprocessor, and the quasi-partitioning scheduling algorithm. Okay, so that's the outline. Okay, basically, these two algorithms solves the problem of scheduling a set of tasks on multiprocessor on symmetric multiprocessor systems, and they are interesting mainly because they are optimal algorithms, so they can solve all the feasible task sets. They are not based on the proportional fairness, so they don't enforce the proportional the progress execution of tasks on the processors, and they are designed to reduce the number of preemption and migrations. And this last characteristic make them to be interesting from the standpoint, from a practical standpoint. Okay. RAN has been presented in 2011 in RTSS, and actually works for periodic tasks, independent and implicit deadline periodic tasks. QPS also works on sporadic tasks, so from theoretical point of view, it's more, it's better than RAN. Okay, we provide a first implementation of an implementation of RAN in 2014 at CRTS in that work, showing that it incurs a moderate overhead, runtime overhead, in between that of a partitioned and global EDF. Okay. So after the presentation of QPS, so we wondered if actually QPS outperform RAN from a practical standpoint. So, roughly speaking, we want to answer if the QPS could be implemented in a more efficient way than RAN. Okay. From an high level point of view, RAN and QPS share some similarities. They work on two phases. An offline phase that actually decomposes the multiprocessor scheduling problem into a set of uniprocessor scheduling problems, and then an online phase that derives a solution for the original multiprocessor scheduling problem, starting from the solution of the uniprocessor scheduling problems. That's okay, the approach. Okay, the two algorithms works on different runtime structures. A reduction tree in the left for run, and a processor hierarchy for QPS. Okay. The reduction tree is computed by the offline phase of run. Okay, and basically requires to solve a bin packing problem. So starting, for example, from a set of tasks, as in figure, with some timing requirements, and the utilization of the tasks. Okay. To that task set is applied bin packing heuristic to basically to aggregate tasks into a server. So the first step, okay, you can see, for example, in this case that the task tau 5 and tau 6 are grouped into a single server S5, and actually the utilization of the server S5 is the sum of the utilization of the single tasks tau 5 and tau 6. And okay, so S5 is actually is still a task, is a virtual task, because it must it have to provide scheduling for its aggregated tasks. Okay. After the packing operation, run perform a dual operation that actually computes the idle time for each aggregated server. It computes the idle time, and that basically is 1 minus the utilization of the aggregated server. And so in this example, we have that set of dual server that are in this case the input for the second application of the packing operation. Okay, so in the end, what we have is that okay, after the dual operation, we start with a new packing operation, so we can aggregate S1 and S2 into S6, S3, S4 into S7, and S5 still have its S8 primal server. Okay, and so on until we get a unit server that basically is the tree, the root of the tree. Okay. The offline, okay, applying packing and dually operations, actually we ensure the convergence of the approach. So we always obtain a unit server at the root of the tree. Okay. On the other hand, QPS still uses packing approach, but it doesn't aggregate tasks into servers. By the way, server, okay, have as a server as an utilization. Okay, the utilization of a server must be lower than 1, obviously. In the QPS, QPS instead aggregates server, but it can, okay, when aggregates, if the system can, I mean the task set cannot be partition it into the processor. Okay, it actually allows some processor to be exceeded in terms of capacity. Okay, and actually to schedule tasks on the systems, in particular on the exceeded processor. It allocates external servers similarly to run. Servers schedules clients, so they are the client tasks into another processor. So in the starting from the same task set as in run, we have that, for example, QPS aggregate task T1 and T2, and in the processor P1 with an exceeding rate of 0.2. Okay, but this exceeding utilization is handled by the server S1 on the processor P3. Okay, so similarly on the processor 2, the exceeding utilization is handled by the server S2. And finally, Tau 5 and Tau 6 are on the same processor P3. Okay, so basically we have that in a processor, we can have server and tasks that are scheduled together. Okay. At runtime, run performs a selection of tasks on the reduction tree that start from the root and propagate down until the leaf of the tree that are actually the tasks that have to be executed at a given time. Okay. So, taking, for example, a snapshot of the reduction tree updated time 3, for example, we have that the root always execute because it's a unit server, so virtually it's virtually allocated to a processor, and have budget and select applying an uniprocessor EDF scheduling policy. One which is in this case the server S6, that is dual in this case. Okay, and so as the server S6 dual is selected, its corresponding primal server is not selected. That's the dual rule schedule. Okay. Since the server S6 is not selected, neither S1 dual, S2 dual are selected, but are selected the corresponding primal servers S1, S2, and therefore Tau1 and Tau2, that are the first two tasks that have to be allocated on the processor. Okay. Similarly, we have S7, S8 that select S3 dual, S5 dual, and so on until the selection Tau4, that is the third task, selected at time 3 to be executed. Okay. The same schedule for QPS at the same time. Okay. What's happened? The server S1 that is the external server of P1 is selected by the processor P3, and the server S1 select one of its client tasks, that is in this case tau 2, and so tau 2 is executed on the processor P3 because S1 is running on the processor P3, okay? And tau 1, that is the other, that is the task running on processor P1, still running in the same processor. Okay, in the processor P2 is allocated the task tau 3, just applying EDF as a scheduling policy. Okay, so P3 and P2 are scheduled by EDF. Instead, okay, and then we have this migration tau 2 into P3 due to the selection of S1. Okay. Then we move into time 5. Okay, as you can see, the budget in red of the task S6. Okay, we have the budget and the earliest deadline of that server is exhausted. So the root of the tree computes a new scheduling operation and selecting this in this case S7 dual. The selection is still propagated down until the selection tau 1, tau 3, and tau 4 that are the tasks that are allocated into the tree processor at time 5. QPS at time 5 instead selects on the processor P3 selects the server S2, and similarly to the time 3, okay, S2 selects the task tau 3 as client, and so the task tau 3 migrates on the processor P3, and whereas okay tau 4 keep running on the processor P2, and P1 is scheduled by EDF. Okay. Okay. When it comes to the implementation, we used a compact representation of the reduction tree to perform the scheduling at the global level or run, so the selection of the tasks according to the algorithm. In this case, the reduction tree only considers the dual nodes. So we compact the data structure, considering only the dual nodes. Each node consists of the earliest deadline computed starting from the client of a given server, okay, and the budget value. It also have a flag to indicate if a node is circled according to the algorithm, okay, and an interval timer that trigger events when the budget exhausted, okay. At the bottom level, okay, the tree, we have the implementation of the server, okay. The first the servers originated by the first packing operation, and in this case we wrap the RT domain object of LITMUS, okay, that comprises a set of I mean, it's a scheduling domain, so it offers queues and for scheduling a set of tasks in a unit processor fashion. So for each server generated by the first packing operation, we instantiate a RT domain that actually contains the aggregated tasks, and it's migrated among processors depending on the requirement, execution, or run. On the other side, we have we still use the RT domain as a basic server implementation, but okay, we don't have a global scheduling data structure. We only have we migrate the RT domain from one processor to another, just okay, according to the algorithm, when the external server selects a task to be executed. In this case, we have the budget values and the interval timer stored in the local processor memory. Okay. And so the main differences from an implementation point of view, as I said, is that in run we have a global scheduling level that express the reduction tree data structure and actually compute the schedule at the virtual level. Okay. The timers that are in the 3 nodes trigger events, and so at each event triggered by timer, a scheduling operation is performed and potentially preemption or migration tasks is executed. And to protect, to ensure the consistency of the reduction tree, to protect from concurrent updating, okay, we expect a global lock, okay. So to perform a scheduling operation, basically we have to acquire the global scheduling lock. Then we can update the reduction tree that will map the RT domain to processors, and when this operation completes, we can schedule with the EDF inside the RT domain. Okay. On the other side, QPS doesn't use global scheduling operations, but still have to synchronize the execution among processor, as because actually we have still to migrate the RT domain, in this case, from when a server is selected from a remote processor. Okay. And okay, the representation of server and tasks. Server and tasks are uniformly represented, so we can perform uniprocessor EDF scheduling inside the RT domain using the same data structure. for tasks and servers. Still, we have budgets must be consistently updated, and still we have time trigger budget consumption events. Okay, but okay, we don't have a global lock here. We only have a lock that involves potentially involve a subset of processor, depending on the processor hierarchy computed offline. Okay. So in the example, okay, I showed before. In this example, okay, in this case we have a single lock because P3 is, the execution of P1, P2 is related to that of P3 because of the server that are activated on P3. But in the general case, we don't have a single lock for QPS, and that's better from overhead point of view. Okay, this figure hints at the fact that we still have some processor synchronization activities to ensure that to guarantees that P1, for example, P1 to P3 executes correctly, and the processor synchronization is performed by using interprocessor interrupt, okay, among processor. So when the server, in this case S1, starts executing on P3, send an interprocessor interrupt on P1 that actually perform, and this interrupt is used by P1 to perform some scheduling activities. In this case, no task selection is performed because T1 can still execute in P1, but in some cases in most of the cases, P1 should perform a preemption in its processor. Okay, what are the main issues we found in implementing running PS? Well, in the run case, okay, we have overlapping events that are time triggers events that are so global events that occur simultaneously because okay, we have independent timer allocated on the tree, and so this overlapping event requires actually trigger 3 updates, but okay, these 3 updates are not necessary actually. So this is an overhead that is so our implementation run incurs this extra overhead because of these overlapping events. Still, similarly in QPS, we can have processor synchronization that doesn't cause any preemptions, and so we can still have an extra overhead due to unnecessary processor synchronization. Another common issues among between run QPS is that we can, during the scheduling, very small scheduling interval maybe originates, and so the budget assigned to each server, okay, and the node to the node of the tree or to the server in the QPS processor, okay. The budget might be lower than smaller than the time required to perform scheduling operation, and this is a very this is very bad from an implementation point of view, because you have to decide if you spend some time to, for example, to migrate a task into another processor, but then you don't have enough budget to actually execute the task on the remote processor. Okay. We perform an empirical evaluation of the implementation of run and QPS. Basically focused on the interference of the scheduling primitives, and we also evaluate we also compare the algorithm in terms of preemption and migration, and we restrict our evaluation only for periodic tasks, because run only schedule periodic tasks actually. But in this case, QPS with periodic tasks must always activate its external server, its remote server. So this is the worst case execution for QPS. It's the worst execution scenario for QPS. Okay, we perform this is the setup. We perform the experiments on a 16-core machines. Actually, we generate the task set randomly, and considering both harmonic and non-harmonic task set, increasing the system utilization from 50% to full utilization, and we generate tasks with different distribution. A distribution that considers only small tasks, that actually favors the beam packing, so the reduction phase, but stress the online phase, because several tasks are basically in the queues, in the scheduling queues. But also we generate a task set considering big tasks to stress the reduction phase and the offline phase. We implemented we first assess the algorithm to gauge the overhead, and then we use the values of the overhead to we determined the overheads for each primitives to be considered as a execution time of tasks, to than to perform the actual evaluation of the system. I don't want you to bother with standard results that you can find in the paper, but this this is the maximum observer execution time for each scheduling primitives. We have a set of 6 in this case for run scheduling primitives. The release of tasks, the scheduling, so that consider also the global scheduling for run, the cost of context switch, the cost of the tick scheduling that actually is not used by those arguments but is considered by our evaluation, the latency of the interrupts, and the cost of single tree update for run. As you can see, in QPS we don't have the cost in to update the reduction tree, and the algorithms are very close from this this evaluation. Again, we have results for the preemption, the migration that the two arguments incur at runtime, and just preemption migration depends on the obviously on the reduction phases. Okay, so in this figure you can see how the depth of the reduction tree and the processor hierarchy increase at the increasing of the system utilization, and that causes an increasing of the number of preemption and migration. Okay, and then we have the cost for the release and the cost for the scheduling primitives, still at the increasing of the system utilization, and finally we have the overall per job overhead, considering all the scheduling primitives, both for heavy tasks and for medium tasks. In this case, you can see that the overhead is almost constant because the algorithm basically, the system is partitioned, is fully partitioned, so the algorithm works as a partitioned EDF. There is no migration of tasks basically. And you can see that close to the full system utilization, QPS is highly penalized by the fact that it's the depth of the processor hierarchy is increases a lot. Okay, and so also the runtime overhead of the scheduling algorithm. Some conclusions. QPS can be implemented extending the implementation of partition EDF, whereas run does not, but it is more susceptible to the offline phase. So it's it's runtime. It's performed better from lower medium utilization. Instead, run exhibits almost a constant overhead. Okay. That's the implementation I the run and QPS, but actually it's not the only one implementation we can provide for that algorithm. And interestingly, we want to consider an implementation that is completely global for both run and QPS, because we think that it's more it's scale on the number of processor basically, but this can be considered a future work. Okay, so I finished.
So we have time for a couple of questions.
Yes.
You can expect that. So actually I'm very sad that I didn't attend the presentation initially last week, because I can see that I would have had a lot of questions to ask.
Yes.
So I'm glad that you presented today. So I'm going to preach for my chapel, if you, as you can expect. So you know UEDF.
Yes.
UEDF is an optimal scheduling algorithm for sporadic tasks, which has been presented the first time 5 years ago. So I'm wondering why you didn't compare QPS with UEDF rather than run, which was only for periodic tasks.
That's an interesting question. I mean, I think that run and QPS share some common traits. Okay. On the fact that they reduce the task set and they create servers that are used at runtime to migrate tasks. Okay. But actually, UEDF I mean, it's I don't have a right answer to this question, because UEDF is still, I mean, it still requires some global scheduling operation. Okay.
Like QPS or like run?
Yes.
Actually, UEDF is much closer from QPS than run, in the sense that you also have a global scheduling operation when new jobs are released. But all the rest of the time, the scheduling operations are just local to the processor also. Worse than that, and that's why I'm really sad that it has not been compared, is that if I look at the results that have been published by the authors of QPS, UEDF in theory, I'm not sure if it is true in practice, UEDF has 5 times less preemptions than QPS and 3 times less migration than QPS when you have the number of processors you used for your experiments.
Okay, and that's I mean, interesting, because the direction, I mean, is to reduce the number of preemption migrations. But as I said, we didn't consider to implement UDF because I mean, when I started implementing QPS, okay, the direction was actually to extend or to generalize the implementation run, but actually we saw that run still incur an overhead that is due to the global scheduling parts, okay? And so I try to implement QPS in a more partitioned way without considering UEDF, but it's I mean, this could be an interesting comparison, actually.
I think that's a comparison that has to be done if you want to have the real opponent to QPS. Also, and that's, I don't know, so I'm going to ask a question. Is QPS, because UEDF has been extended also for open systems. So we don't know all the tasks that are executing from the beginning, and it can handle that without an additional complexity. Is it something that can be done with QPS also?
I would say yes, but it's there are some cases that have to be considered. It's not. We still have a lot of synchronization in the QPS. We still have some issues in the implementation QPS that I think must be solved and can be solved by a completely global implementation of the algorithm, because starting with, if we consider a global implementation or run a global implementation QPS and a global implementation of UDF, I think we can actually make a fair comparison of the algorithm. But in this case, we only provide this evaluation starting from different implementation because we wanted to enhance. Try to get the better from the better implementation from starting from the algorithm formulation. So intuitively, partitioned algorithm is incur a lower overhead than global algorithms. So in QPS we wanted to see when if the partitioned part of the system could actually could benefit the algorithm in terms of runtime overhead, and so that's
what you said is interesting. Then did you compare with, for instance, global EDF or something like that?
We compared run with global EDF, yes.
And QPS?
No, for QPS we don't have a comparison, but actually can be inferred by just looking into the run work, because the set of experiments is almost the same, so you can look the first work or run that compares run with global EDF and partition EDF, and then we have a comparison with run and QPS. So you can.
How does it compare?
Sorry.
How does it compare?
In what sense, sorry?
So in terms of overheads, schedulability.
Yes, the same set of experiments, the same analysis.
No, I mean which one is behaving the best?
In
which conditions?
global and partitioned EDF are not optimal algorithms. So at higher system utilization, they incur in deadline miss. Okay. But in terms of overhead, partitioned EDF is, the best solution. It incurs the lower overhead. But the implementation of QPS is very, very close to that of partitioned EDF when the system is partitioned, because we actually don't have processor synchronization. So we only perform local processor scheduling inside the RT domain, and the RT domain is the same data structure used by the implementation of partitioned EDF. So we don't have extra overhead in terms of on the implementation. So we achieved a very efficient implementation when the system is partitioned, because QPS works exactly as partitioned EDF. Increasing the system utilization, it depends on how many processor synchronization, that in turn depends on the depth of the hierarchy generated offline. And so the more processor synchronization, the more is the overhead, and that's the point. So QPS is better when at lower system utilization. But that's the in practice that's the case, because in hard real-time system we don't have to achieve the full system utilization in general. So
we will stop here, and we'll see you in 2 weeks from now. Thank you again.